All right, our title today is called Putting It All Together, because like I mentioned before, we finished all of the things we need to talk about for curve sketching. We just haven't done it all at the same time. So we need to look through all of the different requirements for our curve sketching algorithm, which look like this. Those are the things that we need to go through, and I suppose number 9 is actually making the graph. Now, when it comes time to do our final test at the end of this unit, I'm going to give you these. So on the front page of the test, it's going to say, do these things. Okay, so that'll help you. You won't have to remember them, but at the same time, you're going to do enough of these you won't forget anyway. So we're going to try and consider all of those different things, make sure that all of the answers that we get for all of those different steps work together so that we can figure out what the final graph should look like. Our attempt this time is this guy. So not a real complicated function, but one that when we look at to begin with, we don't know what it looks like. We have to try and figure out all of the missing pieces and come up with a graph. So 4x minus 4 divided by x squared. That's our target graph. So start off was relatively easy one, I suppose. The y-intercept. So if you want to get the y-intercept, we're just subbing in f of 0. And that's going to turn out pretty nicely because you get that 0 on the bottom. And as soon as you get that 0 on the bottom, our graph's undefined, or excuse me, our y-intercept is undefined. So there is no y-intercept for that graph. And if you think ahead a little bit, that's because there's going to be a vertical asymptote right there. Okay, so there is no y-intercept for this particular function. Okay, so that's not exciting for the graph. X-intercepts. For the x-intercepts, we need to set the function equal to 0. So if we solve that, the x squared is just going to disappear because it's equal to 0. And this solves really nicely. We get an x-intercept of just 1. So only a single x-intercept, and it happens at x equals 1. Here's my picture, and again, I'm cheating a little bit because I know the answer to this, so I know that the graph should look about this size. This isn't an advantage you'll have when you do them for the first time, but it'll help us a little bit today. So I know I have an x-intercept there at x equals 1. So I can start with that, and remember there was no y-intercept, so I don't have that on yet. Vertical asymptote. So we're going to do our vertical asymptotes, then we're going to, and horizontal asymptote. Then we're going to go ahead and talk about the critical and the inflection points after that. So we talked about vertical asymptotes. This happens because we can't allow the denominator. Doesn't look like the way to spell denominator. We can't let the denominator equal 0. And our function had a nice simple denominator actually, it was just that x squared. So we're saying what happens if x squared is equal to 0, and therefore x equals 0. That is our vertical asymptote. So that's good news. All right, in fact, I'm going to go to the graph right away, and I think I'm going to put that on. Here's our vertical asymptote. So we know that, but we don't know is the behavior around the asymptote yet. So I still want to deal with that. What happens as we approach x from the left and x from the right? So as x gets close to 0 from the left, what happens? And as x gets close to 0 from the right, what happens? So here we're thinking of a number getting really close to 0, but negative, right? So like negative 0.001, whereas here we're thinking of a number just bigger than 0. So let's consider the function. And we're thinking about what happens if we sub in a number close to 0. Well, this number on the bottom, that's going to become positive and be really close to, be very small, right? 0 squared, or a number close to 0 squared is very small. This here on the top, the 4x, that gets really close to 0. The minus 4 stays though. Minus 4 stays. So we end up with basically just minus 4 on the top. That 4x is negligible compared to the minus 4. And on the bottom, we have a very small positive number. So minus 4 divided by a really small positive number means we're getting really, really close to negative infinity. Right? Can't get close to negative infinity. We're getting really, really small. We're approaching negative infinity on that one. Similarly, for this guy, it's actually almost exactly the same. This time we're considering a number still approaching 0, but positive. And the thing is, I don't think it matters. Right? It's not significant in this case that it was positive or negative. The 4x part became really small, so we said it hardly mattered at all. And that number on the bottom was x squared, so no matter what, that was becoming a small positive. So the fact that the degree was even has created that positive number on the bottom no matter what. And the minus 4 stays on the top no matter what. So around this asymptote, we're going to be approaching negative infinity both times. So the graph, and I'm going to be a little bit careful sketching this already, but it's going to be doing that on that side and on that side. And that might help a little bit. You can kind of see now how that x-intercept might come into play. That, I think, wrapped up our vertical asymptote, didn't it? Yeah, there was just the one asymptote, and we've considered what happened on either side of it. That takes us to our horizontal asymptote. And with our horizontal asymptote, what we wanted to do is we wanted to consider the degrees, first of all. The tricky one was if the degrees of the numerator and denominator were the same, but they weren't this time. The degree of the denominator is bigger. And since the degree of the denominator was larger, that tells us that the horizontal asymptote was y equals 0. Remember, if the degree of the denominator was ever bigger than the numerator, we had a horizontal asymptote of y equals 0. If the numerator had a bigger degree, there was no asymptote. And if the degrees were the same, that's when we had to do our fancy common factoring trick. So this is good. We know what the horizontal asymptote is. We want to know the end behavior. So what happens if we actually go to negative infinity? And what happens if we go to positive infinity? And remember, this is the one where it was kind of boring. What we did was we just picked a fairly large number and we subbed it into the equation. And what we wanted to see was how it compared to the asymptote. Was it above or below? So if I sub in minus 1,000 into that function, and if we calculate that, make sure you do the calculations carefully. I think I get that. It's a 0 there. And it's not the number itself that's really important. What's important is how it compares to the asymptote. And this is a number that's less than y equals 0, which means that the function itself is approaching the asymptote from below it. Approaching the asymptote from below. If I go to the other side and we sub in the 1,000, same trick, sub in the 1,000, and we still get a number really close to 0, which we should, right? We knew that the asymptote was 0. We should be getting closer and closer to it. But this time I get a number that's a little bit bigger than 0. And so we must be approaching the asymptote from above it this time. So if we take a look at our graph again, let's put in this horizontal asymptote. Now this may or may not bother you. Our horizontal asymptote just went right through our x-intercept. And one of the rules that we usually say for an asymptote is that we can't cross it. Right? We're not allowed to cross an asymptote. And that is absolutely true for a vertical asymptote. For a vertical asymptote, we'll never cross it, which makes sense. It's a function. We're not allowed to cross things like that. But horizontal asymptotes can be crossed. Horizontal asymptotes only really apply for end behavior. We're talking about where the function approaches once x gets really, really big positive or really, really big negative. So that x-intercept right here is okay. It's okay that it's on the asymptote. What matters is way down the road, what happens there. So I can sketch in what's supposed to happen. We knew that as x approached negative infinity, we were approaching the asymptote from below. So the graph's supposed to look something like that. And as we approach, as x gets bigger and bigger positive, it was approaching from above the axis. So it should look like that. So we've got little bits of information that we're sort of adding in as we go. So that takes care of our intercepts, asymptotes, both types. Critical points is next for us. So there was our original function. We're going to calculate the derivative. The one thing that's different now, because we're going to have to go on to a second derivative, it's going to help us to simplify this. So we're going to take the derivative and then go ahead and simplify. This is where I start to recommend using the quotient rule. So remember, you can still use the trick of bringing the x squared up, but the quotient rule will help because things start to simplify for you automatically. Using the quotient rule is the derivative of the top times the bottom minus the derivative of the bottom times the top all over the denominator squared, which would just be x to the fourth. And so on our last test, we would have just left it there, right? We would have said don't simplify, but here I'm going to. Oops. So multiply through that bracket. Collect our like terms. And the one other nice piece, which actually helps an awful lot, there's x's in both terms on the top, so we can cancel one of those with an x from the bottom. So we're left with just that. And that's our simplified first derivative. From there, we'll take our second derivative in a minute. If I want to find the critical points, then we need to set that derivative equal to 0. And the nice part about rational functions is you set them to 0 and the denominator always disappears. So that turns out okay. And we get a nice answer still of just x equals 2. So when x is 2, we're going to have a critical point. We would like to know what the point actually is. And we didn't have to do that for the x-intercepts because they were on the x-axis. But for the critical points, we need to know the y value. So I need to know f of 2. And we're going back to the original function for this. And what's that? 8, 4, that's just 1. So our critical point is 2, 1. So only one critical point. And if we take a look at the graph, I can put that point on there, 2, 1. It's right there. Label that as a critical point. And that looks about right. Even from there, we can maybe start to have a pretty good idea of what this graph should look like. Made sense that we needed to reach a critical point there. That's going to be our local maximum. So critical points are done. remember we have to do our intervals of increase and decrease. And this was mostly about checking and making sure that everything else that we've done is right. So hopefully all the calculations that we get here are going to match with what we are expecting to see when we do the graph. For the intervals of increase and decrease, we have to consider our critical points, and we also have to consider our vertical asymptotes. And we didn't have to do that last time, right? When we did our intervals of increase and decrease with our polynomial graph, it didn't have any vertical asymptotes, so we didn't have to worry about it. But this time, oh, that's not right. It was x equals 2, wasn't it? This time, whenever you have a rational function, we need to consider our vertical asymptotes as well. Because around the asymptotes, you can change from increasing to decreasing. Lots of things change when we hit an asymptote, so we need to include that as we do these intervals. Remember, the intent with the interval was to try and cover everything in the domain. So we start off going everything less than 0, right? Everything left of that vertical asymptote. And then we include the asymptote, because we're including everything in the domain. Then between 0 and 2, between the asymptote and the critical point, include the critical point, and bigger than the critical point. And that now has everything. That includes all possible values of x. Pardon me. Our test value is probably just -1, something less than 0. We don't, oh, I can almost fill this in, right? We don't need a test value for x equals 0. The derivative can't possibly exist here because this was a vertical asymptote. So nothing fancy there. X equals 2, we didn't need a test point because f prime of x was 0 there. That was a critical point. Test value there would be 1. Test value there would be a 3. Now I'm going to use, oh, I can't move that. That was risky. Remember, our derivative was minus 4x plus 8 over x cubed. And what I care about now is when I sub in these test values, remember I don't care about the number, I care about the sign. So if I sub in f prime of -1, the number is insignificant, what's important is the sign. If you want to do the whole calculation, that's obviously fine too, but all I care about is the sign. So I'm looking at it going, on the bottom, it's a negative, and on the top, well, it's a 12 actually, isn't it? So 12 divided by, that's a negative answer. So the key is that we get, you know what, I'm going to put NEG there. That's a negative. And if our derivative is negative, that means that the graph was decreasing. So the graph has to be on its way down for every value of x less than 0. If I sub in f of 1, what happens? Well, the top is 4 divided by 1, so positive here, which means we're increasing. For the 3, it's a minus 12 minus 4 over 27. But again, I don't care. All that I care about is that it's negative there, which means my graph will be decreasing again after that critical point. And so when x equals 2, I know I've gone from an increasing function to a decreasing function. So not only is this a critical point, but now I know that it's a local maximum. So I've figured out a little bit more about it. So just, I'm going to flip to the graph here for a second. We're going to go from decreasing to increasing, hit our maximum, and then be decreasing again. And I think we can kind of see that if we look at it. Going from green to green there, we're going to be decreasing all the way down to that first asymptote. Pick up on the right side of x equals 0. The graph's going to be increasing for a while. Hit the critical point. We'll have a horizontal tangent, and then the graph should be decreasing as we go the rest of the way towards that horizontal asymptote. So there's not much we can add to the graph when we do our intervals. That really is just a way of checking to see how we're doing. Inflection points. To get the inflection points, we want to set the second derivative to 0, which means we need to find the second derivative. Fortunately, the first derivative was already simplified for us. Our first derivative was minus 4x plus 8 over x cubed. So second derivative, we're still using the quotient rule. The derivative of the top is minus 4 times the bottom, minus the derivative of the bottom times the top, all over the denominator squared, which will now be x to the 6. I am still going to simplify that a little bit. I'm going to simplify it, not because I need to take more derivatives, but when I do my intervals of concavity, it's going to be nice to have this part already simplified. Like terms. And you got a whole bunch of x's, so I can cancel actually x squareds out in this one. So it'll just be 8x minus 24. And since I've canceled the x squared, it's just an x to the 4th left. So that's our second derivative right there. I want to set that to 0. And again, it works out okay because that x to the 4th is just going to disappear. And you can solve that pretty quickly just to get our x equals 3. So when x is 3, we're going to have an inflection point. Again, we need to know what the point is. So I need to know the value of f of 3. We have to sub that 3 back into the original function. Original function, remember, was 4x minus 4 over x squared. So that's 8 over 9, which isn't a real nice number. So our inflection point is at 3 and 8 over 9, or just a little bit less than 1. This is actually about the nicest function I've ever found for being able to solve equations. If you think back, we had to solve 3 sets of equations, right? We had to do the x-intercepts, we had to do the first derivative and the second derivative. We had to solve all those. And when we solved them, we got nice answers every time. That will hardly ever happen. To get any sort of interesting function at all, you're almost always going to get at least one of those solutions that's going to have a square root somewhere in it or decimals in it. So don't be surprised when that happens in this unit. I try and set the questions up fairly nicely, but there's often some that there's just nothing we can do about it. Let's add that inflection point to the graph. 3 and 8 over 9. So that's, put it in red. That's about there. That's not perfect, but it's not bad. There's our inflection point. So remember, at our inflection point, that's the location where hopefully the graph is changing its concavity. So we're going to make a switch there from concave down to concave up. So inflection points are done. Final step is actually doing that intervals of concavity. And here we're going to go around our vertical asymptotes again, just like we did in the last one, and our inflection points. For intervals of concavity, we ignore critical points, right? They're not important, but the vertical asymptote still is. So we need to set up our intervals around that vertical asymptote at 0 and the inflection point at 3. Test values can be similar. There's nothing going on here, right? This was our vertical asymptote. Second derivative was 0 there because we have an inflection point. Test value there could be a 1. Test value there could be a 4. And remember, we had already calculated our second derivative. Second derivative was 8x minus 24 over x to the 4th. And we have to sub in these different values. Now, this is the best part right here. The denominator, with it being x to the 4th, it's always positive. So when I was saying before that we don't need to consider the actual value, all we need is the sign, and that becomes more significant here, because all I need to do is consider what happens in the numerator. So if I sub in minus 1 to here, it'll be minus 8, minus 24. It's a minus 32, but again, what's important is that it's negative. I don't care what happens in the denominator. If our second derivative is negative, that tells us that our graph was concave down. At x equals 1, it'll be 8 minus 24, so minus 16. Denominator is always positive. It means this is also negative. So around that vertical asymptote, our concavity didn't change. It's still concave down. But then when we hit our inflection point, we sub in a value of 4. 8 times 4 is 32, take away 24 is 8, so it's a positive number. And so now this is concave up. Remember, what we're hoping for is that all of the answers we got in this chart match all of the other information about critical points and inflection points and intercepts that we'd already put on the graph. So this really was a way to check and make sure that everything else went right. Okay, when you're doing these questions, you're just trying to make sure that all the calculations all balance together, right? Everything needs to fall into place. So hopefully in front of you, you sort of have all those papers, you can see everything at the same time. I've already got the points labeled on, so now it's just completing the rest of the graph. I know that everything to the left of x is 0 was supposed to be decreasing and concave down. And there's no important points in there, so this is just drawn nicely like that and connects. Nothing fancy there at all. But you can see it's concave down everywhere, it's decreasing everywhere, so we're fine. Jump over that vertical asymptote, and this graph was supposed to be increasing until I got to x equals 2. So the graph's increasing, goes through the x-intercept. Remember, the x-intercept isn't significant other than the fact that it's a point as far as curve sketching goes. Then I'm going to come up here, hit the 2, hit x is 2. That's my critical point, that's my maximum. I was supposed to be concave down for all of this, and it still is, right? It's still concave down. I have to go past the 2, still concave down, but now my graph is decreasing. The whole rest of the way I should always be decreasing. This is going to be really hard to draw. I have to hit that inflection point, and technically at that inflection point, I'm switching to concave down, or excuse me, to concave up. And in that little space, that's really hard to show. So it's important that I've labeled it and shown it as an inflection point. I didn't do a terrible job there, but that's difficult to show that we're making that changeover from concave down to concave up at that particular point. And that is our first completed curve sketch of a rational function. There's more to consider with the rational functions with all those asymptotes and things. So, and that's a pretty good one. Remember, we talked there about how the graph was actually going to cross through our horizontal asymptote. So we're allowed to cross the horizontal asymptotes. We can't cross a vertical asymptote. Okay. Here's a little picture. That's what it was actually supposed to look like. Scale's different there, so I've zoomed out a little bit further. But we did great. We did great. That was our point right there. That was 2-1. That was our point right there. That was the 3/8/9. We've got our asymptotes correct. What's kind of interesting, which we can't predict as well using our method, just notice the distance there between the asymptote. That's impossible for us to notice. Well, difficult for us to notice easily. Not something that I'm going to concern myself about, but interesting as you look at the graph, right? The asymptote on the right, or excuse me, the function on the right of the asymptote tends to get a little bit closer to the asymptote faster than the one on the left. Anyway, hopefully that went okay. These are big problems, and we're not used to doing problems this large. So it takes a little bit of practice to get the hang of working through all of the algebra, not making any mistakes, because any mistakes make these really, really tough. You have to do them so carefully so that you don't make any mistakes. And then just trying to put all of the different pieces together so that we get a completed function in the end.